Now that we have written down the Schrödinger equation, we need to see what it means in practice. For this, we will have now a look at quantum mechanical systems in one dimension. So let us sit down and look at this in detail so that we soon can actually calculate something. Our goal will be to solve the Schrödinger equation for a system with a fixed energy. So in the situation where we just have the energy here on the left-hand side, and we want to know what the wave function is at this energy. And on the other side, we use that this is the total energy, which is made out of the sum of the kinetic energy and the potential energy. The kinetic energy, as we have seen in our motivation, involves derivatives with respect to position. And then we have the potential energy, which depends on the problem that we are considering. So this is a differential equation, and just to show you how you might have seen such equations before in another notation, we can write this, of course, a bit more compactly with two dashes for the derivatives, and then v times psi. And as we introduced before, we can also look at this as the Hamiltonian, a certain mathematical operator composed out of all of these operations acting on the wave function. So on the one hand, this is a differential equation, and on the other hand, this is an eigenvalue equation for the Hamiltonian. So when we now want to solve different one-dimensional problems, we are going to make use of some very general features of the Schrödinger equation. The first one is the superposition principle, which is sort of a central principle in quantum mechanics because it highlights the wave nature of the theory inherited from its solutions. This is actually a mathematical feature of the Schrödinger equation, namely because it is linear. We can use certain solutions and combine them together into a new solution. So linear means in this case that the wave function psi always appears in every term just by itself and not as the argument of a more complicated function. For instance, there is no psi squared in these terms or something like this. It is just psi in every term. And because of this, when we have two solutions, psi1 of x and psi2 of x, for any pair of such solutions, if we've already checked that they are indeed solutions, then we can find a more general solution by combining them linearly with two general coefficients a and b, which are just constants. These constants could be real or they could be complex. As it happens, as we have a differential equation of second order, this guarantees us that we have exactly two independent solutions, and then we combine them into the most general solution. However, this solution will not always be physical, and that will be really interesting. So, but before I come to these physical constraints, let's look at another very general mathematical feature, and this concerns the continuity of the solutions. So for all the potentials that we are ever going to encounter, the wave function psi of x itself will be a continuous function. Secondly, in almost all cases, its derivative will also be continuous, with the only exception that there might be some points where the potential is infinite. If there are certain places, and we will actually going to see this in our very first example, where v is infinite at some positions or even some regions, then the wave function can actually have a kink. So if v is infinite at a certain point, then at this particular point psi can have a kink, which means so it can change smoothly and then suddenly change into a different direction as a function of x. Which means exactly that the derivative is actually making a jump at this place. So psi itself might look like this with this kink here, where the derivative is making a jump. So let's look at one more general feature, and this is actually using the physical interpretation of the wave function that we are aiming at, which on the mathematical side concerns the boundary conditions. So as I said before, we start out with a differential equation, which in principle has two independent solutions, but in many cases these solutions will not be the ones that we can allow for physically. And that's because we want to interpret psi squared as the probability density to find the particle somewhere in space. That means that in most cases we would like to have the situation where we can take this probability density and integrate it over all space, and then we would like to get 1 out of this. 1 means that the particle is somewhere. But starting from our mathematical solutions for the moment, we are actually good to say if this integral is at least not infinite and also not vanishing, because then we can adjust the wave function later in a very sensible way and we will get the probability density out of this. That will be just achieved by multiplying the solution by a suitable constant. And if this integral is required to be finite, then we go to very large distances, the wave function will have to go to 0. So if x becomes large either in the positive or in the negative direction. We will encounter one type of solution which is not quite fulfilling this, but we can still allow for this when we suitably adjust our interpretation, so play around with them to make things work. And that will then just require that psi at least remains finite in this limit of large distances. We will discuss the different situations in detail later, but the stricter condition corresponds to certain energy regions where the particle is trapped in space, and we then find only particular energies to be allowed, which is the actual origin of energy quantization. And then we find wave functions that we can really interpret in terms of these probabilities or probability densities. But sometimes we work at energies where the particle can indeed escape to infinity, so it can move through all space, and therefore the condition on the wave function at large distances is somewhat different. And because this condition is not so strict, we then find physical solutions over a whole range of energies, so that in this case energy quantization will not occur. So these are the main mathematical features that we are going to use across all applications in one dimension. And you can already get a feeling how they will translate into very concrete and general physical effects. So as I just mentioned at the beginning, instead of looking at the Schrödinger equation as a differential equation, you can also look at it as an eigenvalue equation. And because the Hamiltonian here is composed out of other operators, this will sometimes help us to find the actual solutions in a problem. First, I just want to mention that because of the special nature of this eigenvalue problem, we are often using a slightly different language for the eigenvalues and the eigenvectors. Because we are looking for energies, we are going to call these energies that appear in specific solutions eigenenergies. And the associated wave functions, we are going to call not only the eigenvectors or eigenfunctions, but also the eigenstates, because they correspond to physical states of the system. Now, the energy is just one of the possible things that you can observe about a quantum system. We already encountered momentum, and momentum is also observable in quantum mechanics. So we had written P as minus IH bar d dx, and so it is useful to think what the eigenstates of this observable are. And they are indeed just the plane waves, e to the IPx divided by h bar, which corresponds to e to the ikx with k determined by the de Broglie rule. Now, in preparation for the situations where we are really going to use the momentum in specific calculations, and these functions in particular, again so that we can extract probabilities without any additional numbers, we are going to include a specific factor in front of this. This is still an eigenfunction, as we will see, and this will just help with our interpretation. Now, for definiteness, I'm going to call this specific function psi p of x, where p is an index that can be any real number, positive numbers meaning the particle moving to the right, and negative numbers meaning the particle moving to the left. So let us briefly check that this is actually still an eigenstate of momentum, for which I calculate minus IH bar d dx of this function psi p. This contains this factor 1 over square root of 2 pi h bar and the factor minus IH bar, which both do not depend on x. so we do not need to care about them when we are then taking the derivative with respect to x. And now we have to take the derivative of the exponential function, which is basically the same procedure as before in the motivation of the Schrödinger equation. And what we get out of this is that according to the chain rule, the factor ip divided by h bar, which in the exponent appears in front of the x, appears at the front of the expression, and then it is just multiplied by this exponential function again. Now we see that these terms that I underline here again make the wave function, and the terms that I have here actually just reduce to p, because minus I cancels with I, and the first h bar cancels with the second h bar, so we just get p multiplied by psi p, which is exactly what we wanted to have. So this is just another example of an eigenstate, but not an eigenstate of fixed energy, but of a fixed momentum. So now you could ask, well, there is another very natural observable that we already mentioned so many times, namely that we are going to see where the particle is in space. So there must be also something like a position operator. So how would this actually look like? Well, the position operator is defined to act on any function psi by multiplying it by the position. But this doesn't mean that any function is an eigenfunction, because we need to put in the arguments, and what we then see is that we have not multiplied by a constant, but this is still at least the definition of the position operator. So this is very straightforward, but the position operator also should have eigenstates, but they're a little bit weird. Okay, so if we want to have an eigenstate, then x times this state, this very specific state, well, this must give you an eigenvalue, and I'm going to call this eigenvalue x naught. I cannot just call it x because x is also the argument. So I need this naught so that we know what we are talking about. And the eigenfunction, the corresponding eigenstate, I'm also giving this index. Right, but if this is the case, then we can again use the definition up here, and then it almost looks like a contradiction. Because if x is not equal to x naught, then psi needs to be 0. So psi x naught for x not equal to x naught must be 0. But that's basically everywhere in space with the exception of a single point. So a lot must happen at this single point. Especially because we want to use this as a probability density. And if this is finite only at a single point, we would never really find anything there, because the region just would be too small. Instead, we need a very singular function. This psi x naught is non-zero only at a single point, but at this point it must be infinitely large. Now, this is not a function actually, but we can still make sense of this if we always place it into a certain context. To write this down, we introduce a symbol, and we call this the Dirac delta function. It is not quite a function, but to think about this, you can always have this little picture here in mind. Right, so we call this the Dirac delta function. And the delta is just the Greek letter delta and is often written like this. And the key property of it is the following, that something very specific happens when you put this delta function into an integral, multiplied by any other function and integrate over space. So let us see what we are actually doing here. We have this delta function and we multiplied it by another function and work out the integral. So now the integrand will be 0 almost everywhere, but for the point x naught, where it will be infinitely large and multiplied by the value of the function at this point. So we can actually use this to make a sensible definition of this integral. And that's all that we need. We are going to say that this will be equal to the value of this function at this point. So for instance, if you replace this function just by 1, so by a constant function, so that you just integrate over the delta function, you would get 1 on the other side. Which means that the delta function is 0 everywhere, but for a certain point, and at this point it is large enough so that the area below it is actually 1. So this is all that we ever going to need about this position eigenstate. But if you prefer another picture, we could also always take a function which is just very high and very narrow, and then take the limit of this situation, making sure that the area always remains fixed to 1. And we will meet a suitable function later in this course. So while the position operator is very simple, its eigenstates are actually quite complicated, but at least they are very localized in space, so they seem to indicate that a particle has a fixed position. But fortunately, when we talk about things happening in position, we can always use the wave function and take its absolute value squared and interpret this as the probability density. So we will always just use psi x squared, perhaps with a suitable adjustment by a constant so that we can identify it with the probability density. So this is a little bit for information. Everything which I've written here is not really needed for your calculations, but it can be defined. And that's important. That's the only thing that you should be taking away from this. It can be defined, and this will be useful when we build the general theory. Right, so what we are really going to use are the general mathematical properties that I discussed before, the superposition principle, the continuity of the wave functions, and the boundary conditions, which will actually help us to determine specific energies in the quantization. And in the problems and the examples that we are going to look at next, indeed also the specific form of the eigenstate for the momentum operator as a tool to find the eigenstates of energy as well. And that's because simply the momentum operator appears in the Hamiltonian. So there are cases where knowing something about the momentum is enough to figure out something about energy. Right, so let's turn to one of these specific examples and see how this goes.